Alpha-decay, or I plus or minus decay, is a type of radioactive decay in which an atomic nucleus emits an alpha particle and thereby transforms into an atom with a mass number 4 less and atomic number 2 less. For example, uranium-238 decaying through I plus or minus particle emission to form thorium-234 can be expressed as, because an alpha particle is the same as the nucleus of a helium-4 atom, consisting of 2 protons and 2 neutrons and thus having mass number 4 and atomic number 2, this can also be written as. Notice how, on either side of the nuclear equation, both the mass number and the atomic number are conserved. The mass number is 238 on the left side and on the right side, and the atomic number is 92 on the left side and on the right side. The alpha particle also has a charge +2, but the charge is usually not written in nuclear equations, which describe nuclear reactions without considering the electrons. This convention is not meant to imply that the nuclei necessarily occur in neutral atoms. Alpha decay typically occurs in the heaviest nuclides. In theory it can occur only in nuclei somewhat heavier than nickel, where overall binding energy per nucleon is no longer a minimum, and the nuclides are therefore unstable towards spontaneous fission-type processes. In practice, this mode of decay has only been observed in nuclides considerably heavier than nickel, with the lightest known alpha emitter being the lightest isotopes of tellurium. Alpha decay is by far the most common form of cluster decay where the parent atom ejects a defined daughter collection of nucleons, leaving another defined product behind. Alpha decay is the most likely cluster decay because of the combined extremely high binding energy and relatively small mass of the helium-4 product nucleus. Alpha decay, like other cluster decays, is fundamentally a quantum tunneling process. Unlike beta decay, alpha decay is governed by the interplay between the nuclear force and the electromagnetic force. Alpha particles have a typical kinetic energy of 5 MeV and a speed of 15,000 km per second. This corresponds to a speed of around 0.05 AC. There is surprisingly small variation around this energy, due to the heavy dependence of the half-life of this process on the energy produced. Because of their relatively large mass, +2 electric charge and relatively low velocity, alpha particles are very likely to interact with other atoms and lose their energy, so their forward motion is effectively stopped within a few centimeters of air. Most of the helium produced on Earth is the result of the alpha decay of underground deposits of minerals containing uranium or thorium. The helium is brought to the surface as a byproduct of natural gas production. History. Alpha particles were first described in the Investigations of Radioactivity by Ernest Rutherford in 1899, and by 1907 they were identified as He2+ ions. For more details of this early work, see Alpha particle history of discovery and use. By 1928, George Gamow had solved the theory of the alpha decay via tunneling. The alpha particle is trapped in a potential well by the nucleus. Classically, it is forbidden to escape, but according to the newly discovered principles of quantum mechanics, it has a tiny probability of tunneling through the barrier and appearing on the other side to escape the nucleus. Gamow solved a model potential for the nucleus and derived, from first principles, a relationship between the half-life of the decay, and the energy of the emission, which had been previously discovered empirically, and was known as the Gigerer-Urey-Nuttall law. Uses: Americium-241, an alpha emitter, is used in smoke detectors. The alpha particles ionize air in an open ion chamber and a small current flows through the ionized air. Smoke particles from fire that enter the chamber reduce the current, triggering the smoke detector's alarm. See smoke detector ionization for details. Alpha decay can provide a safe power source for radioisotope thermoelectric generators used for space probes and artificial heart pacemakers. Alpha decay is much more easily shielded against than other forms of radioactive decay. Plutonium-238, for example, requires only 2.5 mm of lead shielding to protect against unwanted radiation. Static eliminators typically use polonium-210, an alpha emitter, to ionize air, allowing the static cling to more rapidly dissipate. Toxicity: being relatively heavy and positively charged, alpha particles tend to have a very short mean free path, and quickly lose kinetic energy within a short distance of their source. This results in several MeV being deposited in a relatively small volume of material. This increases the chance of cellular damage in cases of internal contamination. In general, external alpha radiation is not harmful since alpha particles are effectively shielded by a few centimeters of air, a piece of paper, or the thin layer of dead skin cells that make up the epidermis. Even touching an alpha source is typically not harmful, though many alpha sources also are accompanied by beta-emitting radio daughters, and alpha emission is also accompanied by gamma photon emission. If substances emitting alpha particles are ingested, inhaled, injected or introduced through the skin, then it could result in a measurable dose. The relative biological effectiveness of alpha radiation is higher than that of beta or gamma radiation. RBE quantifies the ability of radiation to cause certain biological effects, notably either cancer or cell death, for equivalent radiation exposure. The higher value for alpha radiation is generally attributable to the high linear energy transfer coefficient, which is about 1 ionization of a chemical bond for every angstrom of travel by the alpha particle. The RBE has been set at the value of 20 for alpha radiation by various government regulations. The RBE is set at 10 for neutron irradiation, and at 1 for beta radiation and ionizing photons. However, another component of alpha radiation is the recoil of the parent nucleus, termed alpha recoil. Due to the conservation of momentum requiring the parent nucleus to recoil, the effect acts much like the kick of a rifle but when a bullet goes in the opposite direction. This gives a significant amount of energy to the recoiling nucleus, which also causes ionization damage. The total energy of the recoil nucleus is readily calculable, and is roughly the weight of the alpha divided by the weight of the parent times the total energy of the alpha. By some estimates, this might account for most of the internal radiation damage, as the recoil nuclei are typically heavy metals which preferentially collect on the chromosomes. In some studies, this has resulted in RBE approaching 1000 instead of the value used in governmental regulations. The largest natural contributor to public radiation dose is radon, a naturally occurring, radioactive gas found in soil and rock. If the gas is inhaled, some of the radon particles may attach to the inner lining of the lung. These particles continue to decay, emitting alpha particles which can damage cells in the lung tissue. The death of Marie Curie at age 66 from leukemia was probably caused by prolonged exposure to high doses of ionizing radiation, but it is not clear if this was due to alpha radiation or X-rays. Curie worked extensively with radium, which decays into radon, along with other radioactive materials that emit beta and gamma rays. However, Curie also worked with unshielded X-ray tubes during World War I, and analysis of her skeleton during a reburial showed a relatively low level of radioisotope burden. Russian dissident Alexander Litvinenko's 2006 murder by radiation poisoning is thought to have been carried out with polonium-210, an alpha emitter. See also, alpha particle, beta decay, references. Alpha emitters by increasing energy, external links, the Lever chart of nuclides, IAEA with filter on alpha decay with 3 animated examples showing the recoil of daughter.